Turn off the lights, my friend. I am HyperSleep Logs. Together, we're stepping into the deep mysteries of the cosmos. Our journey begins, right now. Imagine standing outside on a clear night. Far from the city. Far from its noise, its glow, its endless motion. You are standing in a field, or perhaps on a hilltop, or maybe on the edge of a quiet desert that stretches out in every direction around you. Above you, the sky is enormous. Not the gray-purple smear you might be used to seeing from a rooftop or a parking lot. This sky is deep. Truly deep. It is black in a way that black almost never is. Not the black of a room with the lights off, not the black of a closed eye. This is the black of genuine, almost infinite distance. And scattered across it, in every direction you can possibly look, are stars. Not a handful of them. Not dozens. Thousands. Tens of thousands. Each one a point of light so faint and so far away that the light entering your eye right now, the photon landing on your retina at this very moment, may have left its source before your grandparents were born. Before their grandparents were born. Before the first recognizable human being ever looked up at this same sky and wondered exactly what you are wondering now. What is all of this? And more to the point, is this all there is? That question, deceptively simple, almost childlike in its phrasing, is one of the most profound questions science has ever attempted to answer. And in recent decades, physicists, cosmologists, and mathematicians have arrived at a possibility so staggering, so genuinely mind-bending, that even the people who believe it most strongly will sometimes admit it feels more like science fiction than science. The possibility is this. Our universe, everything we can observe, everything we can measure, everything we have ever known or touched or imagined, may be just one of an unimaginably vast collection of universes. Not metaphorically. Not as a poetic way of describing the scale of the cosmos we already know. Literally. Physically. Actual, separate universes, each one real, each one complete, each one existing alongside our own in ways we may never be able to directly detect. This idea has a name. We call it the multiverse. Before we can talk about many universes, we need to be very precise about what we mean by one universe. Because the word gets used loosely in everyday language, and when you start dealing with ideas this large, precision matters enormously. When scientists use the word universe, they typically mean the observable universe. This is everything that lies within the cosmic horizon, the boundary in space beyond which light has not had enough time to reach us since the Big Bang, approximately 13.8 billion years ago. That boundary is not a wall. There is no physical edge to the observable universe. It is simply the limit of what we can see. What lies beyond it may be more of the same, more space, more galaxies, more stars, stretching on essentially forever. Or it may be something else entirely. We genuinely do not know. The observable universe is already staggeringly large. Its diameter is approximately 93 billion light-years. If you try to imagine a light-year, the distance light travels in a single year, moving at roughly 300,000 kilometers per second, and then multiplied that by 93 billion, you would arrive at a number so large it has no real meaning in human terms. Within that space, there are an estimated 2 trillion galaxies. Each galaxy contains somewhere between tens of millions and hundreds of billions of stars. Each star may host any number of planets. The total number of stars in the observable universe is estimated at around 200 sextillion. That's a 2 followed by 23 zeros. And all of that, every galaxy, every star, every planet, every atom in every cloud of interstellar gas, that is just one universe. Our universe. The multiverse hypothesis asks us to consider the possibility that beyond our observable horizon, beyond the physics we know, beyond the structures we have mapped and measured, there may be more. Much more. Not more of our universe. Other universes. The idea of multiple worlds is not new. Human beings have entertained it, in various forms, for thousands of years. The ancient Greek philosopher Epicurus, writing in the 3rd century before the Common Era, argued that the universe was infinite and filled with countless worlds, each one formed by chance collisions of tiny, indivisible particles he called atoms. Some of those worlds, he suggested, might be inhabited. Some might even resemble our own. This was not physics in the modern sense. Epicurus had no telescope, no mathematics, no way to test his claims. But the intuition was there, the sense that our world, for all its apparent uniqueness, might be just one expression of something much larger and more varied. In the 16th century, the Italian monk Giordano Bruno took similar ideas and pushed them even further, arguing that the stars we see in the night sky are distant suns, each one potentially surrounded by planets, each one possibly home to life. He was burned at the stake for heresy in 1600. The Church found his ideas not merely wrong but dangerous. For most of scientific history, the question of other worlds remained in the realm of philosophy and speculation. Then, in the 20th century, physics changed everything. 3 separate revolutions in our understanding of the cosmos, quantum mechanics, cosmology, and string theory, each independently gave rise to versions of the multiverse hypothesis. Not because physicists were looking for such an idea. Not because they decided in advance that many universes would be an interesting thing to believe in. But because the mathematics, followed honestly, kept leading them there. To understand the first and perhaps most deeply unsettling version of the multiverse, we need to spend some time in the quantum world. And to do that, we need to let go, just briefly, of the intuitions we have built up through a lifetime of experience with ordinary-sized objects. In the world you inhabit every day, things are where they are. A coffee cup sitting on a table is on the table. Not partially on the table and partially on the floor. Not somewhere between the table and the ceiling. On the table. Its position is definite. Its location is real. At the quantum scale, the scale of electrons, photons, quarks, and the other fundamental particles from which everything is ultimately made, this is not how reality works. At the quantum scale, particles do not have definite positions until they are observed. Before measurement, a particle does not occupy a single location in space. It exists in what physicists call a superposition, a kind of smeared-out cloud of probability, in which the particle is, in some sense, everywhere it could possibly be all at once. This is not a statement about our ignorance. It is not saying that the particle is in a definite place and we simply don't know where. The mathematics of quantum mechanics, a framework that has been tested to extraordinary precision and has never once been found to be wrong, tells us that before measurement, the particle genuinely has no single definite location. It is in multiple states simultaneously. Then you observe it, and suddenly, the particle is somewhere specific. The probability cloud collapses. The multiple possible states resolve into one actual state. The particle is here, not there. This process is called wave function collapse. And for most of the 20th century, physicists accepted it without really asking what it meant. The mathematics worked. The predictions were accurate. The technology built on quantum mechanics, transistors, lasers, MRI machines, solar panels, all of it functioned exactly as the theory predicted. But the question lingered: what actually happens during measurement? What causes the wave function to collapse? And where do all the other possibilities go, the ones that didn't happen? In 1957, a young Princeton physicist named Hugh Everett III proposed a radical answer. Nothing collapses, he said. When you make a measuring NT, when any interaction occurs that forces a quantum system to take on a definite state, the universe does not choose one outcome and discard the others. Instead, it splits. Every possible outcome actually happens. Each one occurs in its own branch of reality, a parallel world that is just as real as the one you are experiencing now but is inaccessible to you, separated from you by the branching structure of quantum events. In Everett's picture, which he called the relative state formulation, and which has since become known as the many worlds interpretation, the universe is constantly, ceaselessly splitting. Every time a quantum event occurs, every time a radioactive atom either decays or doesn't decay, every time a photon hits a beam splitter and could go either left or right, the universe bifurcates. One branch for each possible outcome. The number of branches generated every second is incomprehensible. Not just large. Genuinely beyond any framework we have for thinking about large numbers. Every atom in your body is participating in quantum interactions at all times. Every photon that enters your eye, every chemical reaction in your brain, every heartbeat, all of it is quantum at the lowest level. All of it, in Everett's picture, is constantly branching. Most physicists initially dismissed the idea. It seemed too extravagant, too wasteful. Why would the universe conjure into existence an almost infinite number of parallel copies of itself just to avoid committing to a single outcome? But over the following decades, something interesting happened. As physicists looked more carefully at the mathematics, not just of quantum mechanics but of the universe as a whole, as a closed system, Everett's interpretation began to seem not merely possible but, to many, inevitable. Today, the many worlds interpretation is one of the most widely held views about quantum mechanics among working physicists. Not universal, the debate is genuinely unresolved, but taken seriously, rigorously, by some of the most careful thinkers in modern physics. And if it is correct, then at this very moment, as you listen to these words, as you breathe, as your heart beats, there are other versions of you. In other branches of the wave function. Living other lives. Making other choices. Existing in worlds that diverged from yours at some quantum juncture so small and so distant that neither version of you would be able to identify exactly when the split occurred. The many worlds interpretation is perhaps the most philosophically provocative version of the multiverse idea. But it is not the only one. And for many cosmologists, it is not even the most compelling. To understand a different kind of multiverse, one that emerges not from quantum mechanics but from cosmology, from our best understanding of how the universe was born, we need to go back to the very beginning. The Big Bang. The Big Bang is often described as an explosion. This is understandable but slightly misleading. It was not an explosion of matter into pre-existing empty space. There was no pre-existing space. The Big Bang was the beginning of space itself, and of time, and of everything in it. What we know is this: roughly 13.8 billion years ago, the universe was in an extraordinarily hot, dense state. All the matter and energy that exists today was compressed into a volume unimaginably smaller than a single atom. From that state, the universe began to expand. It has been expanding ever since. It is expanding right now, as you listen to this. But there is a problem with the simple version of this story. And it was noticed in the late 1970s, by a physicist named Alan Guth, who was at the time working late nights at Stanford, wrestling with a seemingly obscure technical problem in particle physics. The problem was this: the universe, when we look at it in every direction, is remarkably uniform. The temperature of the cosmic microwave background radiation, the faint glow of ancient light left over from the early universe, is almost exactly the same in every direction we look. Not approximately the same. Almost exactly the same. The variations are 1 part in 100,000. In a universe that expanded slowly from a hot, dense point, this should be impossible. Regions of space that are far apart from each other could never have been in contact, could never have exchanged heat, could never have had time to reach the same temperature. Yet somehow, they have. The universe looks as though it was once all one thing, all the same temperature, all the same density, all perfectly smooth. Guth's solution was breathtaking in its simplicity and terrifying in its implications. In the very first fraction of a second after the Big Bang, a fraction so tiny it makes a nanosecond look like an eternity, the universe underwent a period of exponential expansion. Not the gradual expansion we see today, but an explosive doubling and redoubling of the fabric of space itself, driven by a strange form of energy that Guth called the inflating field. During this period of inflation, the universe grew from something smaller than a proton to something roughly the size of a marble, in approximately 10 to the power of -32 seconds. To put that in perspective, 1/10,000,000th of a trillionth of a trillionth of a trillionth of a second. This solved the horizon problem beautifully. Before inflation, the entire observable universe was a tiny, causally connected region, everything in contact with everything else, able to exchange heat and reach a uniform temperature. Inflation then stretched that tiny region to cosmic scales in an instant, explaining why the universe looks the same in every direction. But here is where the multiverse enters the picture. The inflating field, like all fields in quantum mechanics, is subject to quantum fluctuations. It does not behave smoothly and identically everywhere. In different regions of space, quantum randomness means the field will behave slightly differently. In most regions, the field decays and inflation ends, giving rise to a hot, dense region, what we would recognize as a Big Bang, the beginning of a universe like ours. But in other regions, the field doesn't decay yet. It keeps inflating. It keeps generating space, faster than the inflation in neighboring regions can catch up. This process, which cosmologists call eternal inflation, means that once inflation starts, it never truly stops. It keeps going, forever, in some region of the larger space. And as it continues, it produces bubble after bubble of space that stop inflating and instead undergo a hot Big Bang of their own. Each bubble is a universe. Our universe, everything we can observe, all 93 billion light-years of it, is one bubble in an eternally inflating foam of universes. Each bubble is separated from the others by regions of still inflating space that are expanding faster than light, making it impossible for any information to ever travel from one bubble to another. These other universes would be real. They would exist in the same physical sense that our universe exists. They would be made of matter and energy. They would have stars and galaxies, or something analogous, depending on the physical constants that govern them. But we could never see them, never communicate with them, never confirm their existence by direct observation. This is what physicist Max Tegmark calls the Level 2 multiverse. And it follows, almost inevitably, from the best model we have for how our universe began. There is something about our universe that, once you notice it, becomes impossible to ignore. It appears to be fine-tuned for life. Not in a vague, impressionistic way. In a precise, quantifiable, almost suspicious way. The fundamental constants of physics, the numbers that determine the strength of gravity, the charge of an electron, the mass of a proton, the rate at which the universe expands, these constants have specific values. And if those values were even slightly different, not dramatically different, but slightly, the universe as we know it could not exist. Consider gravity. It is the weakest of the four fundamental forces. Much weaker than electromagnetism, much weaker than the nuclear forces. If gravity were only slightly stronger, if the gravitational constant were a fraction larger than it is, stars would burn out in thousands of years instead of billions. Complex chemistry, the evolution of life, the development of intelligence, none of it would have time to happen. If gravity were slightly weaker, matter would never have coalesced into stars and galaxies at all. The universe would be a thin, cold, featureless soup of hydrogen and helium, expanding forever without ever forming the structures that make complexity possible. Consider the strong nuclear force, the force that binds protons and neutrons together in the nucleus of an atom. If it were slightly weaker, atomic nuclei would fly apart. Atoms heavier than hydrogen could not exist. No carbon, no oxygen, no nitrogen, the elements on which all life as we know it is built. If the strong force were slightly stronger, protons and neutrons would bind so tightly that the universe would consist almost entirely of a single element, probably helium or some heavier isotope, and the rich chemistry of life would once again be impossible. Consider the cosmological constant, the term in Einstein's equations of general relativity that represents the energy density of empty space. Its observed value is extraordinarily small. Absurdly small, by the standards of theoretical physics. Calculations suggest it should be enormous, a number so large that if the cosmological constant had the value that most physical theories naively predict, the universe would have blown itself apart in a fraction of a second after the Big Bang, long before any structure could form. Instead, it is almost exactly zero. Not quite zero, we can measure a small positive value, which is causing the universe's expansion to slowly accelerate, but almost exactly zero. So close to zero that physicists have spent decades trying to understand why. The list goes on. The ratio of the electromagnetic force to gravity, the masses of the quarks, the number of large spatial dimensions, free, just enough for stable orbits, just enough for complex three-dimensional structures, not so many that gravity becomes too weak to form stars. All of these constants appear to be set, with extraordinary precision, to values that permit a complex, life-bearing universe. There are essentially three ways to respond to this observation. The first is to say it is a coincidence. The universe has the values it has. We happen to be here to observe it. No further explanation is needed or possible. The second is to say it is evidence of design, that the constants were deliberately chosen by some intelligence for the purpose of creating a universe capable of supporting life. This is a philosophical and theological argument, and science has little to say about it directly. The third is the multiverse. If there are many universes, perhaps an enormous number of them, each one with slightly different values of the fundamental constants, then it is not surprising that we find ourselves in one where the constants are right for life. We could only find ourselves in such a universe. Universes with the wrong constants would have no observers to notice them. The fact that we observe a life-permitting universe is therefore not evidence of anything special about our universe. It is simply a consequence of our existence. This argument is known as the anthropic principle. And when combined with the idea of eternal inflation, which naturally produces a vast ensemble of universes with different physical properties, it offers a potential scientific explanation for what otherwise looks like cosmic coincidence. Not everyone finds this satisfying. Some physicists argue that the anthropic principle is not really an explanation at all, that it simply relocates the mystery rather than resolving it. Others argue that fine-tuning is overstated, that there may be many possible configurations of constants that could give rise to complexity, and that we are drawing conclusions from a sample of exactly one observable universe. The debate is unresolved. And it is one of the deepest and most genuinely difficult debates in all of science. In the late 20th century, a theory emerged that many physicists hoped would become the final unified description of all of physics. A theory that would reconcile quantum mechanics with general relativity, the two great pillars of modern physics that have, stubbornly, refused to fit together. That theory is string theory. The core idea of string theory is elegant to the point of poetry. What if the fundamental constituents of the universe are not point particles, not tiny, dimensionless dots of matter, but tiny, one-dimensional vibrating strings? What if electrons and quarks and photons and all the rest are not different kinds of things, but different modes of vibration of the same underlying object? Just as a guitar string can vibrate at different frequencies to produce different musical notes, a fundamental string vibrating in different ways would manifest as different particles. The mass, charge, and other properties of a particle would be determined by the frequency and pattern of its vibration. The mathematics of string theory turned out to be extraordinarily rich. Disturbingly rich. Among the predictions it made was the existence of extra dimensions, spatial dimensions beyond the three we can perceive, curled up at scales too small to detect, present in the structure of spacetime but invisible to any experiment we can currently perform. The original version of string theory required 10 spacetime dimensions. Later versions required 11. The 3 large spatial dimensions we experience, plus time, plus 6 or 7 additional dimensions, compacted down to scales near the Planck length, approximately 10 to the power of negative 35 meters, so small it has never been and perhaps never will be directly probed. Those extra dimensions, being small and compact, can be arranged in an enormous variety of different configurations, different shapes, different topologies, different sizes. Each different configuration would give rise to different physics, different values of the fundamental constants, different particles, different forces, different rules. When physicists began counting the number of possible configurations, they arrived at a number that has since become famous, or perhaps infamous, in the world of theoretical physics. 10 to the power of 500. That is not a large number. That phrase, large number, does not come close to capturing what this means. 1 followed by 500 zeros. To give you a sense of scale, the total number of particles in the observable universe is approximately 10 to the power of 80. 10 to the 500 is larger than that by a factor so enormous it defies any attempt at analogy. Each of those configurations corresponds to a possible universe, a possible vacuum state, in the language of physics, with its own set of physical laws. This collection of possible universes is called the string theory landscape. And here is where it connects to inflation. In the eternal inflation picture, as different regions of the inflaton field decay, they don't all decay to the same vacuum state. They decay to different points on the string theory landscape. Each bubble universe that forms has a different compactification of the extra dimensions, and therefore different physics. The result is a multiverse of almost unimaginable variety. Not just many universes each governed by fundamentally different physical laws, with different particles, different forces, different structures of spacetime itself. Some of those universes would be utterly empty, no structure, no complexity, no possibility of anything interesting happening. Others would collapse in an instant, crushed by overwhelming gravity. Others would fly apart so fast that no 2 atoms would ever come close enough to form a molecule. And somewhere in that landscape, perhaps in a relatively small fraction of the total, but a fraction that still corresponds to an incomprehensibly large number of universes, there would be universes like ours. Universes where the constants happen to be in the range where stars can shine and planets can form and chemistry can become biology and biology can become thought. String theory is not a complete theory. It has not yet made a definitive prediction that has been tested and confirmed by experiment. Its extra dimensions have never been observed. Many physicists remain skeptical of it, or have moved on to other approaches. But the landscape it describes, if it is real, would represent the most dramatic expansion of our conception of reality in the history of human thought. There is one more version of the multiverse that deserves attention. It is perhaps the most audacious of all, not because it requires new physics or exotic fields or extra dimensions, but because it requires a fundamental rethinking of what we mean by reality itself. It is the idea proposed by physicist and cosmologist Max Tegmark, and he calls it the mathematical universe hypothesis. Tegmark begins with an observation that most physicists take for granted without examining it too closely: the universe is described by mathematics. Not approximately described. not loosely modeled by mathematics, but described with extraordinary precision at every level, from the equations of quantum mechanics to the curvature of spacetime. Why should this be? Why should the physical world be so perfectly captured by abstract mathematical structures? Physicist Eugene Wigner famously called this the unreasonable effectiveness of mathematics in the natural sciences. It is unreasonable because there is no obvious reason why the universe should be mathematical. Why should abstract patterns, invented or discovered by human minds wrestling with pure logic, turn out to describe the behavior of physical reality? Tegmark's answer is both radical and, in a certain light, almost obvious. The universe is not described by mathematics. The universe is mathematics, not a metaphor, a literal claim. Our universe is a mathematical structure, a collection of abstract relationships and symmetries, and we, the conscious beings within it, experience that structure from the inside as physical reality. If this is true, then there is no reason why our particular mathematical structure should be the only one that exists. Every consistent mathematical structure would, by the same logic, be equally real. It would be arbitrary and inexplicable for only one mathematical structure to have physical existence. The more natural conclusion, uncomfortable as it is that all of them do. This is what Tegmark calls the level 4 multiverse, the ultimate ensemble, in which every possible mathematical structure is a real universe. Not just universes with different physical constants. Not just universes with different particles. Universes with entirely different mathematical foundations. Universes with different numbers of dimensions, different topologies, different fundamental symmetries. Universes whose rules are so different from ours that we have no words for what they contain. It is an idea that most physicists find either profound or absurd, and sometimes both at the same time. If Tegmark is right, then the question is not why our universe has the properties it does. The question dissolves. Every possible set of properties exists. We experience ours because we are in it. The mystery of fine-tuning is resolved not by appeal to a designer or to mere luck, but by the recognition that all mathematically possible universes are equally real, and we, inevitably, find ourselves in one compatible with our existence. It is an extraordinary idea, and whether you find it liberating or vertiginous probably says something about how you relate to mathematics itself. Every version of the multiverse hypothesis faces a common objection, and it is a serious one. It comes not from the realm of physics, but from the philosophy of science. The objection is this: if other universes are truly beyond any possible observation, if no measurement we could ever make could confirm or refute their existence, then is the multiverse a scientific hypothesis at all? Or is it something else, philosophy, perhaps, or metaphysics, or wishful thinking dressed in the language of physics? The philosopher Karl Popper gave us what has become the most widely cited criterion for scientific claims. A claim is scientific if it is falsifiable, if there is, in principle, some observation that could prove it wrong. Hypotheses that can accommodate any possible observation, that make no definite predictions about what we will or won't find, are not doing science. They are doing something else. By this criterion, many versions of the multiverse are in trouble. If there is no way to see another bubble universe, no signal that could reach us from a parallel branch of the wave function, no experiment that could probe the string theory landscape, then how is proposing their existence different from proposing the existence of undetectable angels? Defenders of the multiverse take several approaches to this challenge. The first is to question the criterion itself. Falsifiability is a useful guide, but it has never been a hard boundary of science. There are many things we accept as scientific: the existence of other galaxies, the nature of the interior of black holes, the conditions at the very first moments of the Big Bang, that we cannot directly observe and could not falsify by any experiment currently conceivable. Science routinely makes inferences beyond what can be directly seen. The second approach is to argue that the multiverse does make testable predictions, just indirect ones. If eternal inflation is real, it should have left specific imprints on the cosmic microwave background. Some theorists have predicted that bubble universes might occasionally collide with ours, leaving detectable signatures in the distribution of temperature across the sky. So far, no such signatures have been conclusively found. But the search continues, and if they were found, it would be extraordinary evidence for the inflationary multiverse. The many worlds interpretation, similarly, does not add new predictions to quantum mechanics. It is, in a technical sense, empirically equivalent to the standard Copenhagen interpretation. But it makes no additional claims that could be falsified, and it does correctly describe every quantum experiment ever performed. The third approach is more philosophical, to argue that if a theory's equations describe something, then that thing is real, even if we cannot observe it directly. If the equations of eternal inflation inevitably produce bubble universes, and if those equations correctly describe the universe we can see, then denying the reality of the other bubbles requires an arbitrary act of metaphysical restriction, deciding that only the bits we can observe are real, while everything else, even if described by the same equations, is fictional. There is no consensus here. Physicists who take the multiverse seriously are not naive. They are acutely aware of the testability problem. They argue about it constantly. And the honest ones will admit that they don't fully know how to resolve it. What is clear is that the multiverse is not the result of wishful thinking, or of science fiction, or of a desire to make the universe seem more interesting than it is. It emerges, again and again, from some of the most carefully developed and empirically successful theories in the history of science. It is an uncomfortable consequence of mathematics followed honestly to its conclusions. Let us set aside, for a moment, the technical debates. Let us set aside falsifiability in string landscapes and wave functions. And let us just sit with the idea. If there are other universes, what might be in them? In the level 1 multiverse, the simplest version, in which space simply extends beyond our observable horizon, following the same physical laws, the contents would be, in some sense, familiar. Stars, galaxies, planets, atoms. The same particles, the same forces, the same chemistry. But arranged differently, because the quantum fluctuations that gave rise to structure in our universe would have played out differently in those distant regions. In a universe large enough, and the eternal inflation picture suggests they may be almost infinitely large, every possible arrangement of matter that is consistent with the laws of physics must eventually occur. Every possible pattern. Every possible configuration of atoms. Including this one. Including you. Including this exact planet, this exact solar system, this exact arrangement of stars in this exact galaxy, replicated somewhere, enormously far away, perhaps to the point of being indistinguishable from the universe you know. Physicists can actually calculate an estimate of how far away such a copy might be. The result, assuming the universe is infinite and matter is distributed according to a random process, is approximately 10 to the power of 10 to the power of 28 meters. That number is so large it makes the observable universe seem like a rounding error. But if space is truly infinite, and if the same physics operates everywhere, then such copies are not merely possible. They are, in a rigorous statistical sense, inevitable. In the bubble universes of eternal inflation, the situation is more varied. Those universes may have different values of the fundamental constants, different physical laws. Some might have more stable forms of matter. Some might have faster or slower chemistry. Some might have conditions so alien that the word life would need to be reimagined entirely before it could apply to anything that lives there. In the string landscape, the variety becomes incomprehensible. Universes with different numbers of particle types, different structures of spacetime, different rules for how energy is stored and exchanged. Perhaps universes in which nothing we would recognize as complexity ever develops, empty, stable, forever uniform. And in Tegmark's ultimate ensemble, the range of possibility is total. Every mathematical structure that can exist, does exist. Including structures so unlike anything we have ever thought of that we have no conceptual tools to imagine them. What we can say, with some confidence, is that if the multiverse is real, then life, wherever it arises, will only arise in universes that permit it. The fine-tuning problem dissolves not because our universe is special, but because the universes where life cannot arise have no one in them to ask why they are the way they are. There is something that science does, which philosophy does not always do, and which religion has historically been reluctant to do. It tells you when it doesn't know. The multiverse sits at the very edge of what we know. It sits, in fact, at the edge of what we can know, at least with the tools currently available to us. This is an uncomfortable place for science to be. Science thrives on measurement, on experiment, on the ability to say, here is a prediction, here is a test, and here is what we found. Science has given us antibiotics and transistors and vaccines and satellites. It has let us see the surfaces of other planets, image the shadows of black holes, detect the gravitational waves from colliding neutron stars in galaxies a billion light-years away. All of that power comes from the rigor of the method. From the insistence that ideas must be tested. From the willingness to discard a theory, no matter how beautiful, if the evidence does not support it. The multiverse has not yet been tested. Perhaps it cannot be, with current technology. Perhaps it can never be, by any technology imaginable within our current understanding of physics. And yet, the history of science is full of moments when the limits of knowledge turned out to be not permanent walls but temporary horizons, horizons that receded as we developed new tools, new methods, new ways of asking questions. For most of human history, the question of what stars were made of was considered permanently beyond human knowledge. The philosopher Auguste Comte, writing in the 19th century, used the chemical composition of stars as his example of a question science would never be able to answer. Stars were too far away. We could never visit them, never collect a sample, never perform a chemical analysis. Within decades, spectroscopy, the analysis of the light stars emit, had given us exactly that. A complete catalog of the elements present in any star, readable from a distance of millions of light years, simply by examining the wavelengths of the light it produces. Perhaps the multiverse will remain forever beyond our reach. Perhaps the horizon will never recede. Or perhaps, in some future era, physicists will find a method we cannot yet imagine, some new observable, some subtle signature, some mathematical structure that connects our universe to its neighbors in a way that leaves an imprint we can actually detect. We do not know. And acknowledging that we do not know is not a weakness of science. It is its greatest strength. If the multiverse is real, what does it mean for how we understand ourselves? For how we understand meaning, and uniqueness, and the significance of any individual life? These are not questions physics can answer. They are questions each of us must answer for ourselves. But it is worth sitting with them for a moment. One reaction to the multiverse is a feeling of diminishment. If there are infinitely many other universes, each one just as real as ours, each one home to an unimaginable variety of experiences and beings and events, then in what sense does anything here matter? In what sense is any choice meaningful, any achievement significant, any moment precious? But consider the alternative reaction. If this universe, our universe, is the only one, then every event that has ever happened here is uniquely, irreplaceably significant. Every star that has ever shone, every species that has ever evolved, every person who has ever lived and loved and wondered and suffered, all of it has happened exactly once, in the only cosmos that exists, and when it is over forever. Perhaps that is more diminishing still. Or perhaps the multiverse offers a different kind of consolation. If every possible version of events plays out somewhere, if every choice you might have made has been made in some branch of the wave function, if every moment that you experienced is part of a vastness that includes all moments, then perhaps nothing is ever truly lost. Perhaps experience, in some deep sense, is conserved. These are not scientific claims. They are philosophical ones. But physics has always had this quality. At its frontiers, it bleeds into philosophy. The deepest questions about the nature of reality are questions that both physicists and philosophers must face, and neither discipline has all the answers. What the multiverse does, perhaps above all else, is remind us how much we do not know. How provisional our picture of reality is. How much of what we take for granted, the solidity of the world, the uniqueness of our universe, the finality of the choices we make, may be, at the deepest level, not what it seems. Science is not done by theories in the abstract. It is done by people, often obsessive, sometimes brilliant, occasionally wrong, always human. The story of the multiverse is in large part the story of a handful of individuals who were willing to follow an idea further than it was comfortable to go. Hugh Everett III was 27 years old when he wrote his doctoral dissertation at Princeton proposing what would become the many worlds interpretation. His advisor, John Wheeler, admired the work but was troubled by its implications. Wheeler eventually distanced himself from it. The physics community was largely dismissive. Everett left academia, took a defense industry job, and never published seriously on physics again. He died in 1982 at the age of 51, never knowing that his ideas would be taken seriously, let alone that they would eventually become one of the leading interpretations of quantum mechanics. His daughter later said he had believed he would live to see the vindication of his theory. He did not. Alan Guth was 32 when he stayed late in the lab on the night of December 6, 1979, and worked out the implications of what he called the inflationary scenario. He wrote in his notebook that it was a spectacular realization. The word spectacular was underlined twice. The inflationary model Guth developed has since been refined and modified by others, including Andre Linde, who developed what is called chaotic inflation, the framework most naturally suited to producing an eternal multiverse. Linde still works today, still passionate about ideas he has spent 4 decades developing. Max Tegmark has been described as the most openly enthusiastic advocate of the multiverse in contemporary physics. He holds a position at MIT. He gives public lectures. He writes books for general audiences. He is genuinely, visibly delighted by the ideas he works with, and that delight, for anyone who encounters it, is contagious. These are not mystics or dreamers. They are rigorous mathematicians who began with concrete physical problems and found, at the end of their equations, something they had not expected and could not deny. Much of what we know about the early universe, about inflation, about the conditions that gave rise to everything we see, we have learned from a faint whisper of radiation that fills the entire sky. The cosmic microwave background, or CMB, is the oldest light in the universe. It was emitted approximately 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine into hydrogen atoms, allowing photons to travel freely for the first time. Before that moment, the universe was opaque, a dense plasma through which light could not pass. After that moment, the universe became transparent, and the light that was released then has been traveling ever since. We detect it today as a faint microwave radiation coming from every direction in the sky, at a temperature of approximately 2.7 degrees above absolute zero. The CMB is remarkably uniform, but not perfectly so. There are tiny fluctuations, variations in temperature of about 1 part in 100,000, that map the distribution of matter in the early universe. Those fluctuations are the seeds from which all the large-scale structure of the cosmos, all the galaxies and galaxy clusters we see today, eventually grew. The pattern of those fluctuations is a direct consequence of quantum mechanics in the early universe. The tiny quantum fluctuations in the inflaton field were stretched to cosmic scales by inflation, imprinting a specific statistical pattern on the CMB. That pattern, described by what physicists call the power spectrum, is one of the most precisely measured quantities in all of science. And it matches, with extraordinary accuracy, the predictions of inflationary cosmology. This is significant. It means that the quantum fluctuations of the inflationary period, the same process that, according to the eternal inflation picture, continuously generates new bubble universes, are real, and have real, measurable consequences in our universe. The Planck satellite, launched by the European Space Agency in 2009, measured the CMB with unprecedented precision. Its data confirmed the inflationary picture in remarkable detail, and provided no evidence against it. Future missions, ground-based telescopes, next-generation space observatories, will continue to refine our picture of the CMB, looking for any anomalies that might hint at something beyond the standard inflationary model. Some researchers have claimed to see hints in the CMB data of exactly the kind of collision signature that would be expected if our bubble universe had, at some point in its history, grazed another bubble. These claims remain controversial. Other researchers, examining the same data, do not find compelling evidence for such a collision. The question is genuinely open. In 1998, two independent teams of astronomers made a discovery that changed our understanding of the universe's destiny. They have been studying a particular type of exploding star, a type Ia supernova, which produces a predictable amount of light, making it possible to use as a standard candle to measure cosmic distances. By comparing how bright these supernovae appeared to how bright they were expected to be at various distances, the teams were mapping the rate at which the universe had been expanding over its history. The expectation was that gravity, the mutual attraction of all the matter in the universe, would be slowly decelerating the expansion over time. The universe was born in the hot, explosive Big Bang, but gravity should, over billions of years, be putting the brakes on. Perhaps eventually halting the expansion. Perhaps even reversing it, leading to what cosmologists call the Big Crunch, a final catastrophic recollapse. Instead, the supernovae told a different story. The universe is not slowing down. It is speeding up. The expansion of the universe is accelerating. Distant galaxies are moving away from us not more slowly with time, but more quickly. Something is pushing outward. Something is overcoming the gravitational pull of all the matter in the universe and driving the cosmic expansion to accelerate. That something was given a name, dark energy. And its nature remains one of the deepest unsolved problems in all of physics. The leading candidate is the cosmological constant, the energy of empty space. Even empty space, it appears, is not truly empty. It has an intrinsic energy density, a kind of baseline pressure, that drives expansion. That energy density is extraordinarily small, a tiny positive value rather than the enormous positive or negative value that most theoretical predictions would suggest. But it is there. And it dominates the universe's destiny. If dark energy continues to drive accelerating expansion, and current observations suggest it will, then the universe faces a slow, cold, lonely end. Over hundreds of billions of years, galaxies will drift farther and farther apart. Stars will exhaust their fuel and go dark. Eventually, even black holes will evaporate, leaving a universe of almost perfect emptiness, expanding forever toward a maximum entropy, a cosmic stillness so profound it is almost peaceful. This is the fate of our bubble universe. But in the eternal inflation picture, it is just one story in a library of stories that never ends. Other bubbles are being born even as ours ages and cools. Other universes are beginning their stories. The vast, inflating substrate continues, indifferent to the quiet endings of the bubbles it has produced. There is one aspect of the multiverse that most physicists prefer not to dwell on for too long, because it leads very quickly into territory where physics shades into philosophy and philosophy shades into something altogether stranger. The question of consciousness. In the many worlds interpretation, every time a quantum event occurs, the universe branches. The branches are all real. The beings in each branch are all real. But each being, each version of you, in each branch, experiences only one outcome. Each version of you has a continuous subjective experience, a sense of being a specific person in a specific world, even though from the outside there is no collapse, no selection, no fact of the matter about which branch is the real one. How does this work? How does a subjective, first-person experience arise from a quantum wave function that contains all possible outcomes simultaneously? This is a form of what philosophers call the hard problem of consciousness, the question of how physical processes give rise to subjective experience, but intensified almost beyond endurance by the multiverse context. Some physicists argue that consciousness itself is the key to understanding quantum mechanics. The Copenhagen interpretation, in some of its formulations, seems to suggest that a conscious observer is necessary to collapse the wave function, that reality is not definite until a mind perceives it. This interpretation has largely fallen out of favor among physicists, who are uncomfortable with the idea that consciousness plays a fundamental role in physical law. Others argue that consciousness is simply a particularly complex pattern of information processing, that the sense of being a specific, continuous self arises from the way information is organized in a brain, and that in the many worlds picture, each branch contains a complete, fully functional pattern of this kind. The question of which branch you are in is simply not a well-defined question. But there is a deeper discomfort here that no amount of philosophical sophistication quite resolves. In a universe, or multiverse, where every possible outcome is real, where every choice has been made somewhere, where every version of every event plays out in some branch, what is the status of agency? What is the status of moral responsibility? If, in some branch of the wave function, you make the worst possible choice you can imagine, and you do, because every possible choice is made somewhere, does that affect the significance of the choices you make here, in this branch, in this version of reality? Most physicists would say no. The branches are causally disconnected. What happens in one has no effect on another. The version of you in this branch is not relieved of responsibility by the existence of other versions. The choices you make here are the choices that shape this reality, the only one you can inhabit or affect. But the question lingers. And it lingers not because it is unanswerable, but because it is the kind of question that changes the way you think about your life even before you have arrived at an answer. Where does the multiverse stand in the scientific community today? The honest answer is contested, but serious. The inflationary multiverse, the bubble universe picture that emerges from eternal inflation, is taken seriously by a large fraction of cosmologists. It follows from the inflationary model, which is itself supported by strong observational evidence. The question of whether eternal inflation is inevitable given the basic inflationary picture is still debated. Some modifications of inflation do not lead to eternal inflation, but many do. The many worlds interpretation of quantum mechanics has, over the past few decades, become increasingly mainstream. Surveys of physicists about their preferred interpretation of quantum mechanics consistently show many worlds as one of the top answers, often rivaling or exceeding the old Copenhagen consensus. Physicists at institutions like Oxford, where philosopher David Deutsch and physicist David Wallace have done extensive theoretical work on it, treat it as the most natural reading of the quantum formalism. String theory, and the landscape of possible vacua it predicts, remains controversial. There are physicists, including Nobel laureate David Gross, and the brilliant theorist Nima Arkani Hamed, who hold sharply different views on whether the landscape is a genuine physical prediction or a sign that string theory has gone wrong somewhere. The debate is real, and it is not close to being resolved. What has changed over the past 40 years is the tone of the discussion. Multiverse ideas are no longer automatically dismissed as unscientific speculation. They are debated in the pages of the most prestigious physics journals. They are the subject of textbooks. They are taught in graduate courses. This does not mean they are correct. The history of science includes many beautiful ideas that turned out to be wrong. The multiverse may be one of them. But it is taken seriously by serious people, for serious reasons. And that, in science, is where progress begins. It is late now. Wherever you are, the world outside may be quiet. The city, if there is one, may have settled. The traffic has thinned. The people who fill your day have found their way to their own dark rooms, their own pillows, their own private silences. And out there, above your ceiling, above your clouds, above the thin blanket of air that separates the living world from the void, the universe continues. The stars continue. The galaxies drift apart at a velocity that grows with every passing second. The quantum events that branch the wave function continue to branch, silently, at every point in space, at every moment in time. Whether there are other universes or not, whether the multiverse is real or a beautiful fiction, none of that changes this moment. This room. This breath. But it changes something about how the moment feels, when you hold it up against the vastness that either contains it or surrounds it. There is a kind of vertigo that comes from looking honestly at the scale of things. Not fear, exactly. Something more like awe, the recognition that the world is so much larger, and so much stranger, than anything you could have imagined on your own. Science is the practice of following that strangeness wherever it leads. Of refusing to stop asking questions just because the questions become uncomfortable. Of building, carefully and incrementally, a picture of reality that is truer than the one you started with, knowing that the picture will always be incomplete, always in need of revision, always pointing towards something you haven't understood yet. The multiverse is where some of that following has led. It may not be the final answer. It may not be an answer at all, in the sense that we usually mean by that word. It may be, in the end, a question that opens into other questions, into a regress of strangeness that the human mind will spend centuries slowly learning to inhabit. That is all right. That is, in fact, exactly what science is supposed to do. Before we close, it is worth bringing together the 4 distinct types of multiverse that we have encountered, each one arising from different physical reasoning, each one making different claims about the nature of reality. Physicist Max Tegmark has organized these into a classification that has become widely used in the field. Level 1, the simplest multiverse. If space is infinite, and if the distribution of matter follows the same statistical rules everywhere, then it distances enormously beyond our observable horizon. Every possible arrangement of matter must eventually repeat. There are other versions of Earth. Other versions of you. Not in another dimension, not in another kind of space, just very, very far away. This is perhaps the least exotic of the multiverse proposals, and it follows from assumptions that many cosmologists already accept. Level 2, the bubble universe multiverse of eternal inflation. Different regions of the inflating substrate stop inflating at different times and settle into different physical configurations. Each bubble has its own Big Bang, its own physics, its own version of the fundamental constants. These bubbles are separated by expanding space that moves faster than light, making them permanently inaccessible to one another. Level 3. The many worlds multiverse of quantum mechanics. Every quantum event branches the wave function. Every possible outcome of every quantum measurement exists in some branch. The branches are equally real but mutually non-communicating. This is not a cosmological multiverse. It requires no special conditions about the large-scale structure of the universe. It follows simply from taking mechanics at face value, without adding any additional mechanism to cause the wave function to collapse. Level 4. The mathematical multiverse of Tegmark's hypothesis. Every consistent mathematical structure exists as a physical reality. Our universe is one such structure, a particular set of equations and symmetries experienced from the inside. All other consistent mathematical structures are equally real. This is the most speculative of the 4 levels, and the most difficult to test or falsify by any conceivable means. These 4 levels are not competing hypotheses. They may all be simultaneously true. If the mathematical universe hypothesis is correct, then it includes the others as special cases. If eternal inflation is correct, it naturally gives rise to level 2, and each level 2 bubble contains a level 3 many worlds branching. Level 1 follows if space is infinite within any single bubble. Or perhaps none of them are correct. Perhaps the universe is finite and alone. Perhaps the quantum wave function really does collapse, for reasons we don't yet understand. Perhaps the constants are not fine-tuned after all, or are determined by some deeper principle we haven't discovered yet. Science does not promise answers. It promises a method, the most reliable method human beings have ever developed, for getting closer to the truth, one careful step at a time. We began tonight with a night sky, with the particular quality of silence that you find only far from other people, when the air is still and the darkness is real and the stars are so numerous they begin to seem not like individual points of light but like a single luminous field that wraps around you on all sides. That sky, ancient, vast, indifferent, beautiful, has been above human beings for as long as there have been human beings. Our ancestors looked at it and saw gods, and stories, and maps for navigation, and portents of what was to come. They gave names to its patterns. They built temples aligned to its turnings. They navigated oceans by it. They planted crops by it. They measured their lives against it. And now we look at it and see something almost stranger than any myth, the possibility that what we see is a single window in a house of infinite rooms. That the cosmos we inhabit is one expression of a principle so generative, so inexhaustible, that it has produced, or is producing, everything that could possibly exist. That is not a diminishment of the sky above you. If anything, it is an expansion. Not the sky becoming smaller, more familiar, less mysterious, but becoming incomprehensibly larger than you thought. The mystery growing, not shrinking, as our knowledge grows. This is the gift that physics gives, when you follow it long enough, not answers that close questions, but answers that open into larger questions, that reveal a universe stranger and richer and more astonishing than the one you thought you were living in. The light of distant stars takes millions of years to reach your eye. The photon that lands on your retina tonight may have left its source before the first human being ever walked on Earth. It has crossed an emptiness we have no words for, at a speed that is the fastest thing in the universe, and it has arrived here, in this moment, to become a small part of your experience of being alive. If the multiverse is real, that same star, that same point of light, exists in uncountable other branches of the wave function, in uncountable other bubble universes, in an uncountable variety of mathematical structures. All of those instantiations are real. All of them are happening. And yet this one, this photon, this eye, this moment, is the one you are in. The one you are. That, perhaps, is enough to sit with for now. The questions will still be there tomorrow. The universe will continue its expansion. The quantum events will continue to branch. The inflaton field, if it exists, will continue its work in the regions beyond our horizon. And you will continue, too, through sleep and into the next day, carrying with you, perhaps, some faint residue of the strangeness we have traveled through tonight. Some lingering sense that the world you will wake up in is larger and more mysterious than the one you usually allow yourself to inhabit. Sleep well. The universe is very old and very patient and extraordinarily strange. There is a single experiment in physics that Richard Feynman once described as containing the entire mystery of quantum mechanics. Not an overstatement. Not a rhetorical flourish. A precise, accurate description of a phenomenon so strange that no one, not physicists, not philosophers, not anyone, has fully made peace with what it means. The double-slit experiment. Here is the setup. You take a barrier with two narrow slits cut into it, side by side. Behind it, you place a detector screen that records where particles land. Then you fire particles, electrons, say, one at a time, toward the barrier. If electrons were simple, classical, billiard ball-like objects, the result would be obvious. Each electron would go through one slit or the other. Over time, you would build up two bands of hits on the detector screen, one band behind each slit. Two piles. That is not what happens. What you get instead is an interference pattern. Not two bands, but many alternating bands of high and low counts, a pattern characteristic of waves, not particles. Waves from the two slits overlap and interfere, like ripples on a pond. Where the crests of the two waves coincide, you get bright bands. Where a crest meets a trough, you get darkness. This would be unremarkable if electrons were waves. But here is where the strangeness begins. If you make the source weak enough to fire electrons one at a time, so that there is never more than a single electron in the apparatus at any given moment, you still get the interference pattern. Not immediately, but gradually, as more and more electrons accumulate, the same banded pattern emerges. Each individual electron interferes with itself. Each electron, somehow, goes through both slits simultaneously. Not through one and not the other, through both. It travels as a wave of probability, spread out across space, until it is detected at the screen. At that point, the wave function collapses. The electron appears at a specific location. but the probability of where it appears is determined by the interference of the wave function passing through both slits at once. Now here is where the mystery deepens. What if you add a detector at one of the slits, a device that tells you which slit the electron went through? Not a device that physically blocks the electron. Just a device that records information about which path it took. The interference pattern disappears. Immediately. Completely. The moment information about which path the electron took becomes available, even if no one reads that information, even if the data is never looked at, the interference vanishes. You get two bands. The electron is now choosing one path or the other. The act of measuring, of obtaining information about which path was taken, changes the behavior of the electron. Reality itself, at the quantum level, responds to the act of knowing. In the many worlds picture, this is explained without paradox. When the path measuring device interacts with the electron, the two become entangled, their wave functions merge into a single combined wave function. The universe branches. In one branch, the electron went left and the detector recorded left. In another branch, the electron went right and the detector recorded right. There is no mystery about the disappearance of interference. Each branch sees a classical particle following a definite path. The interference only occurs when the two paths remain coherently combined in a single branch of the wave function. This is why many worlds is so appealing to many physicists. It provides a consistent, mathematically complete picture of quantum mechanics without invoking SPE. Seil rules about observers, without asking what measurement really means, without appealing to any process of collapse that the equations themselves don't describe. The cost is many worlds. The benefit is clarity. Whether that is a bargain worth making is, as we have seen, deeply contested. There is another aspect of quantum mechanics that the multiverse picture helps clarify, and that, on its own, is one of the strangest phenomena in all of science. Quantum entanglement. When two particles interact in certain ways, they become entangled. Their quantum states become correlated in a way that persists even when the particles are separated by vast distances. Measure a property of one particle, and you instantly know the corresponding property of the other, no matter how far apart they are. Einstein famously found this deeply troubling. He called it spooky action at a distance and spent years arguing that it must reflect some hidden classical variables, some pre-existing correlation established when the particles interacted, that would explain the correlation without invoking any mysterious instantaneous connection. In 1964, physicist John Bell derived a mathematical inequality, now called Bell's inequality, that would hold if Einstein were right. If hidden variables determined the outcomes in advance, certain statistical correlations between measurements on entangled particles could not exceed a specific threshold. Experiments, beginning with the landmark tests in Paris in the early 1980s and continuing with increasingly precise experiments right up to the present day, have shown that Bell's inequality is violated. The correlations exceed the threshold. Einstein's hidden variables don't work. The spooky action is real. And yet no information travels faster than light. No signal is sent from one particle to the other. The correlation is real, but it cannot be used to communicate. It is as though the two particles are different aspects of a single thing, even when separated, as though the apparent individuality of particles is, at some level, an illusion. In the many worlds picture, entanglement is not mysterious at all. Entangled particles are described by a single combined wave function. When you measure one, you and the particle become entangled with it. The universe branches. In each branch, the correlated outcome of the other particle is consistent with the outcome in that branch. The correlation is not sent anywhere. It is a consequence of the branching structure of a single, universal wave function. This might seem like a technical distinction, but it points towards something important about the many worlds picture. It treats the universe as a whole, a single entity, a single wave function, rather than a collection of individual particles that occasionally interact. In this view, the fundamental object is not the particle, not the field, but the universe itself, in its entirety, in all its branches. And if that is the fundamental object, then perhaps it is not surprising that the universe's quantum structure leads naturally to a multiverse. Perhaps the multiverse is not something added on top of quantum mechanics, but something that follows inevitably from taking quantum mechanics with the seriousness it deserves. One of the most common objections to the many worlds interpretation is this: if the universe is constantly branching, why don't we see it? Why do we experience a single, classical, definite world, rather than a superposition of all possible worlds? The answer involves a process called decoherence. And it is one of the most important ideas in modern quantum physics. Quantum superpositions, states where a particle is simultaneously in multiple states at once, are fragile. Extraordinarily fragile. They are preserved only when a quantum system is completely isolated from its environment. Any interaction with the outside world, any exchange of energy, any absorption or emission of a photon, any collision with a neighboring particle, causes the quantum system to become entangled with the environment. Once entangled with a large environment, the system behaves as if it has collapsed, as if it has taken on a single definite state. The different components of its wave function no longer interfere with each other in any detectable way. They become, for all practical purposes, separate classical worlds. This is decoherence, the process by which quantum superpositions become effectively classical through interaction with the environment. For macroscopic objects, a chair, a person, a planet, decoherence is essentially instantaneous. The environment is so large and the interactions so numerous that any quantum superposition decoheres in a time far shorter than we can measure. This is why you don't walk through walls. Why Schrödinger's cat is not actually in a superposition of alive and dead. At the macroscopic scale, decoherence ensures that the world looks classical. The quantum branching happens, but the branches separate so quickly and completely that there is no way for beings within one branch to detect the others. Decoherence does not, technically, solve the measurement problem. It does not explain which branch becomes the real one, because in the many worlds picture, there is no single real one. But it does explain why we perceive a classical, definite world even if the underlying reality is quantum and branching. Understanding decoherence was a major step forward in quantum physics, developed primarily in the 1970s and 1980s by physicists including Heinz-Dieter Zeh and Wojciech Zurek. It transformed the many worlds interpretation from a philosophical curiosity into a framework that could actually explain our experience of the world, why we seek definite outcomes, why we don't walk through walls, why the cat is definitely alive or definitely dead when we open the box. The branches are real, but decoherence ensures they are functionally separate, like stories in the same book that can never cross over into each other's pages. There is one more deep puzzle that the multiverse illuminates in an interesting way. A puzzle so fundamental that it touches not just physics but our entire experience of being alive. The arrow of time. The laws of physics, at their most fundamental level, are time-symmetric. The equations of quantum mechanics, of electromagnetism, of general relativity, all of them work equally well in both directions of time. There is no mathematical reason why time must flow forward rather than backward. The equations don't know the difference. And yet time has a very clear direction in our experience. The past is fixed and the future is open. Eggs break and do not unbreak. Heat flows from hot to cold, never from cold to hot. Memories are of things that have already happened, not things that are yet to happen. The universe began in a state of extraordinary low entropy, extraordinary order, and has been moving toward higher entropy, greater disorder, ever since. This directionality, the thermodynamic arrow of time, follows from the second law of thermodynamics. Entropy always increases. Systems naturally evolve from ordered to disordered states. But this only explains why entropy increases from whatever state the universe started in. It doesn't explain why the universe started in such an extraordinarily low entropy state to begin with. This is one of the deepest questions in all of physics. And the multiverse offers a potential, if not entirely satisfying, answer. In a universe that has existed for an infinite time, or in a multiverse with an effectively infinite variety of possible initial states, a low entropy beginning is not special, it is just one of the many starting conditions in the ensemble. We find ourselves in a universe that began with low entropy for the same reason we find ourselves in a universe with life-permitting constants. Any universe without a low entropy beginning would have no organized structures, no ordered processes, no life, and therefore no OB. Servers to ask why the universe is the way it is. This is another application of the anthropic principle. And like most applications of the anthropic principle, it is simultaneously illuminating and slightly unsatisfying. It tells you why you observe what you observe, but it does not feel like the deep, physical explanation you were hoping for. Perhaps the deepest explanation for the arrow of time is still waiting to be discovered. Perhaps it requires not just a multiverse, but a deeper understanding of time itself, an understanding we don't yet have. Cosmologist Sean Carroll has argued that the low-entropy initial state of our universe might be explained by a spontaneous quantum fluctuation from a much higher entropy parent space, a kind of eternal background from which baby universes can be born, each one beginning with low entropy relative to its surroundings. This is speculative, and Carroll himself acknowledges the uncertainties. But it represents the kind of thinking that the multiverse inspires, a willingness to take seriously the possibility that our universe is not self-contained, not self-explanatory, but embedded in something larger. There is something profound about the concept of a cosmological horizon. Not a wall. Not an edge. Just a limit, a distance beyond which the universe becomes permanently inaccessible to us, not because of any physical barrier, but because of the geometry of spacetime itself. Our observable universe has a radius of about 46 billion light-years. Light from anything farther than that has not had time to reach us in the 13.8 billion years since the Big Bang. As the universe expands, New regions come into view at one edge of the observable horizon, but other regions, on the far side of the expansion, recede beyond it. In a universe with accelerating expansion, which is the universe we appear to live in, the cosmological horizon will eventually stop growing. Eventually, the accelerating expansion will carry most of the observable galaxies beyond our horizon. The Milky Way and the local group of galaxies closest to us will remain gravitationally bound. But everything else will recede, slowly but irreversibly, beyond the point where any signal from them can reach us. In the far future, trillions of years from now, observers in our galaxy will see a night sky with fewer and fewer galaxies. Then none. Then just our local group, slowly exhausting itself, surrounded by an emptiness that stretches out to the horizon and beyond, hiding everything that used to be visible. What will those future beings think, looking at that stripped sky? They will have no way to infer the existence of the billions of galaxies that were once observable. The universe will appear to them much smaller, much simpler, much more isolated than it actually is. The evidence that would have told them about the greater cosmos will have vanished beyond the horizon. This thought is both humbling and clarifying. We are extraordinarily lucky to live in this particular epoch, early enough in the universe's history that the evidence of its large-scale structure is still visible, still accessible, still telling its story to anyone with a telescope and the patience to listen. And perhaps we are equally lucky, or unlucky, depending on your temperament, to live close enough to the beginning of physics that the evidence for whatever lies beyond our universe has not yet been entirely hidden from us. Perhaps there are faint signatures in the cosmic microwave background, faint anomalies in the large-scale structure of the cosmos, that whisper of what lies beyond the horizon we can see. Perhaps not. The universe keeps its secrets well. If you have stayed with this journey from the beginning, if you have listened through the quantum worlds and the bubble universes and the string landscape and the mathematics that underlies everything, then you have done something genuinely difficult. You have held in your mind, simultaneously, the smallness of your own life and the staggering vastness of what that life is embedded in. You have entertained ideas that resist visualization, that strain language, that ask you to accept as possibly real things that no human being will ever directly see. That is not nothing. That is, in fact, one of the most distinctively human things there is. The capacity to hold a question that is larger than yourself. To sit with uncertainty without demanding it resolve. To find, in the not knowing, something that feels not like failure but like the beginning of understanding. The multiverse may be real. It may not be. The question may remain open for a very long time. Possibly forever. But the asking of it, the honest, rigorous, patient asking of it, has already changed how we understand the universe. Already revealed depths that would otherwise have remained hidden. Already demonstrated, once again, that reality is under no obligation to be what we expect. And now, rest. The questions will wait. They are very patient. Almost as patient as the universe itself. Every era of science has its frontier. The border between the known and the unknown shifts slowly, sometimes dramatically, as new instruments are built, new mathematics developed, new questions asked with sufficient precision. In the 17th century, the frontier was the solar system. Whether the planets moved around the Earth or the Sun. whether the heavens were made of the same matter as the earth or of some special, incorruptible fifth element. Those questions, revolutionary in their time, heretical to some, now seem almost quaint. We have sent spacecraft to every planet in the solar system. We have landed on Mars. We have flown past Pluto. In the 19th century, the frontier included the nature of light. Whether it was a particle or a wave. Whether it required a medium to travel through, the luminiferous ether, physicists called it, or could propagate through empty space. The answer, when it came, overturned expectations entirely. Light is neither purely wave nor purely particle, but something that requires a new framework, quantum mechanics, to describe properly. In the 20th century, the frontier expanded to the very large and the very small simultaneously. General relativity described space and time as a single flexible fabric, curved by mass and energy. Quantum mechanics described the behavior of the very small, the subatomic world of particles and fields and probabilities. Both theories worked extraordinarily well in their respective domains. Neither theory was complete on its own, and they refused to fit together. That unification, the marriage of quantum mechanics and general relativity, remains the central unsolved problem of theoretical physics today. String theory is one attempt at it. Loop quantum gravity is another. There are others still, less well known, perhaps less developed, perhaps containing seeds of an approach that will eventually succeed. The multiverse sits at this frontier. It is, in a sense, a consequence of taking both quantum mechanics and cosmology seriously, of asking what happens when you apply the rules of quantum physics not just to particles in a laboratory, but to the universe as a whole. Perhaps the answer, when it comes, will make the multiverse unnecessary. Perhaps a theory of quantum gravity will resolve the measurement problem, explain the arrow of time, determine the values of the fundamental constants, and render the multiverse hypothesis superfluous. Perhaps the universe will turn out to be finite and alone after all, and the constants will turn out to be determined by some deep mathematical principle we haven't yet understood. Or perhaps the multiverse will turn out to be not an hypothesis, but a theorem. A mathematical consequence of whatever final theory emerges, inescapable, as real as any other prediction, as fundamental as the speed of light or the charge of the electron. We are standing at the edge of what is known. And the view from here, in every direction, is extraordinary.